In the second part of our third module on linear kinematics, we're going to take a focused examination of a sample activity, and that's the 100-meter dash, and we will focus on some of the performance numbers for two of the historically top performers in this event, Shelly-Ann Fraser-Pryce and Usain Bolt. And so in this particular type of task, two commonly used measures, variables to quantify performance is something called stride rate, which relates to the number of strides that are completed per second. And so the term stride rate indicates a time rate of change of these strides, and the horizontal ground distance is defines stride length as the linear distance for every stride, which is defined as the heel contact to heel contact of the same leg as that leg cycles through motion. So running speed is equal to stride rate times stride length, as that product will define that performance of that particular athlete. Now, it's important to note here that stride rate and stride length are not exclusive to the 100-meter dash. These are definitions and variables that would quantify any type of ambulatory movement, and are common variables to examine, for example, in older adults that are functionally limited but are still able to ambulate over ground. The equation at the bottom illustrates this definition of running speed, in which the strides per second is multiplied by the meters per stride, which is the stride rate, times the stride length. The stride unit cancels out, and so we're left with meters per second. If we examine those two separate variables, where SL is stride length, SF is stride frequency, which is a commonly interchangeable term with stride rate, these data were obtained from the results of the 2009 Athletics World Championships, subsequently published in the association report in 2011. And so these are data that describes these two variables in the top three finishers, the gold, silver, and bronze medalists in Fraser-Pryce, Jeter, and Stewart. So if we focus first on the total number of strides taken by the top three finishers, here we see the gold medal finalist here, the gold medal winner in Shelly-Ann Fraser-Pryce, having the greatest number of strides compared to the the silver and bronze medalist. The 20 to 40 meter interval for stride length and stride frequency is notable, since typically this represents approximately the point in the 100-meter dash where athletes achieve their peak horizontal velocity. But one pattern that emerges here, will focus first on the gold medal finisher. We see that stride length continues to increase from 0 to 20 to 20 to 40, and then plateaus between the 40 and 100-meter mark, at 2.19, 2.18, and 2.2. In terms of stride frequency, we see that the gold medal winner achieved a peak stride frequency at this point in the race of 4.91, decreased to 4.82, increased a little bit over that over the 60 to 80 meter mark, but then dropped considerably in the last 20 meters, as it did for the silver and bronze medalists. So if we focus on stride frequency for the silver medalist, she achieved a stride frequency of 4.7 in the 20 to 40 meter. That decreased to 4.65, further decreased to 4.62, and then dropped considerably in the last 20 meters, as it did for the bronze medal finisher. So even though the 100 meters is a relatively short distance, athletes do experience a considerable amount of fatigue, as illustrated in the consistent drop in the stride frequency in the final 20 meters of the race. And this this will define the overall performance variable, kinematic performance variable that we'll see on subsequent slides. So I would encourage you to click these YouTube links to watch that actual race and to watch a training run for the gold medal finisher in that race that are captured in 2 still images on this slide. But when we start to quantify linear kinematics, we always have to start with a reference. And so the reference here is the position at the start line. And so we would define the initial position as 0 meters and define the initial time as 0 seconds. At a point later on, after the athlete began moving, this athlete achieved a position of 20 meters in 3.03 seconds, and by using the velocity equation of the final position, subtract the initial position, divided by the final time, subtract the initial time, we see that if we substitute the numbers, understanding that we're taking the displacement divided by the change in time, remember, we always begin the equation with the final and we subtract the initial for both the numerator and the denominator, and that gives us a positive velocity value of 6.60 meters per second. Note that the V symbol for velocity has a bar on top indicating that this is an average velocity over this period of time and over this distance. So certainly once the athlete began moving, her velocity was certainly not 6.6 meters per second. At the 20 meter mark, she's moving considerably faster than 6.60 meters per second. So it's important that we understand that when performing a calculation such as this, we're getting a single value to represent the performance over that 20 meter distance. And so the 6.60 meters per second would represent an average at roughly around the 10 meter mark. So we're going to take a look at one factor that could potentially influence performance in an event like this, and that's something called reaction time. So reaction time is defined as the period of time in seconds or milliseconds, depending. Various sources will use either one of these 2 units to describe reaction time, elapsed between some stimulus, and in the 100 meter dash, the stimulus is auditory in nature, and a conscious motor response. The key term here is the motor response, so there's some sort of kinematic behavior that is occurring. So if we examine the 100 meter dash results for the male athletes, this table here captures the reaction time after the start, at the instant of the start of the race. So here we see the top 3 finishers, the gold, silver, and bronze medalist. Here we see their respective reaction times, and we see the reaction times of the remaining athletes in that final race. So when we take a look at what factors into this reaction time, it always begins with some sort of auditory signal. But because the starter is standing at some distance, once that starting gun goes off, then the sound produced by that gun generates vibrations within the air molecules, which then travels to the ear and then reverberates in the middle ear against something called the tympanic membrane, which is analogous to a drum, banging a musical drum. And when that membrane reverberates, it causes movement in very small bones within the inner ear. And those very small movements of those bones will generate action potentials. Okay, so these are the sound waves that are coming in. These sound waves, which are vibrations in the air molecules, will reverberate that tympanic membrane and then will produce action potentials that travels along the vestibular cochlear nerve that terminates within the temporal region of the brain. And then once that sensory signal is perceived, then the athletes will generate the motor response that you see illustrated in this photograph here. So the motor response here will follow the pattern of activating upper motor neurons, which will activate lower motor neurons, which will activate muscle fibers that will produce a mechanical response and movement. And so this table here illustrates the results of not just reaction time that we saw on the previous slide, but also the 100-meter performance time of all of the 8 male athletes at those 2009 World Championships. And so, just as a reminder, when we calculate velocity, it's going to be that displacement divided by the change in time, but we're going to take a more focused view of this relationship between overall performance in the time to complete the 100-meter dash and that initial point, that reaction time. So this figure here illustrates that relationship between those two measures on the previous slide. But first we'll take a look at some of the statistics of those 8 athletes. And so the average reaction time for the 8 male athletes was 0.139 seconds, but if we go back one slide, we see that no athlete achieved a reaction time of 0.139 seconds. So it's important to remember that when we calculate a mean or an average value, it doesn't represent the value that all the samples obtained. It represents just that, an average. The just as important and arguably more important than the average is the measure that describes how spread out those scores are, and that's the standard deviation. The CV is referred to as a coefficient of variation, which is a percent value of how much variation exists among those 8 athletes. And in this case, the reaction time varied on average of about 11% among all 8 athletes. In terms of the average 100-meter time, the average performance was 9.92 seconds. And so once again, if we go back one slide, we see that no single athlete achieved a time of 9.92 seconds. Two athletes came very close to 9.92, but no athlete achieved that time. So that is just an average of all 8. The standard deviation was 0.23 seconds with a coefficient of variation of only 2.27 seconds. So in terms of the overall performance of the event, we see a very tight distribution among those 8 athletes for that performance time. However, in terms of the reaction time, we see a much greater value. Now this graph at the bottom is going to highlight that relationship between reaction time and 100-meter time. This is important because it begins to answer the question of whether having a very fast reaction at the beginning of the race will translate into a better performance. And so reaction time in this instance is acting as a predictor. So can the reaction time predict that 100-meter time in that race? And so what we see here, we see a cluster of data that follows a particular pattern. And for now, I'm just going to ignore these 2 points that are sticking out away from this cluster of data. And so when we examine this cluster, we see a general pattern that we can quantify as something called a line of best fit. And so this line is directed in what we call an inverse manner. So an inverse relation is defined by a line that describes the change in one variable with respect to the other variable. So the inverse relation we see as the values, as the magnitude along the x-axis increases, the value along the y-axis decreases. And so in this particular relation, a slower reaction time, so as you move from the left to the right, the larger numbers indicates a greater delay from the auditory signal to movement. That means the athlete is reacting slower, is actually related to a better 100-meter time. So this is a conclusion that these data are telling us. However, from a training and 100-meter performance perspective, this seems counterintuitive, where the athletes that had the faster reaction times down here had worse performance. We also see these 2 points out here that don't seem to follow this pattern here. So this point out here that we see deviates vertically in terms of 100-meter time is called an outlier. And an outlier is defined as a point that has a large vertical deviation. As you can see along the x-axis, this point, although this person has the slowest reaction time, it's not very far from this central cluster of data along the x-axis. But it deviates considerably in terms of the 100-meter performance along the y-axis. This point is not per se defined as an outlier, although it appears as an outlier. It is by definition called a leverage point. And a leverage point is defined as one that has a large horizontal deviation. So if you examine the 100-meter performance for this point, draw it along to where it hits the y-axis, we see that it fits very well with this cluster. It's on this top end of the cluster, but it's still contained within this cluster. However, along the x-axis, we see that it does have a rather considerable distance from this bottom part. So when we talk about describing the entire kinematic pattern of the 100-meter dash, we begin by asking the question, what is the velocity at the instant the starter's pistol is fired? Well, we set that starting position at the start line as our 0 position. So the change in position over a very, very small period of time is 0 meters. And the change in time is we can just arbitrarily take 100 milliseconds. And so the change in position over the change in time is going to translate into a 0 velocity because the athlete has not moved from that starting point. So what we see here we see the respective times at 10 seconds, or rather at the respective points in the race. So at the 10-meter mark, 20, 30, all the way up to the 100-meter mark, we see that the gold medal winner covered the first 10 meters in 1.88 seconds, the same time as the bronze medalist, but then began to cover those distances in a shorter period of time. So if we examine the kinematic pattern, what we see here we see time placed along the x-axis, position along the y-axis. And so we're going to first start by highlighting that very initial part of the 100-meter dash. And so this slide is essentially a zooming in of the first second and the first 10 meters. So the reaction time of the gold medal winner, Usain Bolt, was measured to be 0.146 seconds. And so that's going to occur over this very small interval of time that we see here. So here we see the full 1 second. Here we see out to 10 meters. But if we track the change in distance over that 0.146 seconds, so the position at time 0, of course, is going to be 0. The position at t less than 0.146 is also going to be 0. So we know the velocity, as long as you're not moving, velocity is going to be 0. And this is going to highlight one approach in examining kinematics without using any equations, and that's called the graphical method. So the graphical method always places time along the x-axis. And so in biomechanics, at least with kinematics, time is always going to be our independent variable, the variable that is placed along the x-axis. And so we always start with position, because really that's what we're doing here. We're tracking the position with respect to the reference point, which is the start line, all the way through as time moves from left to right. And so this is just a hypothetical kinematic tracing of a 100-meter performance of one athlete. And so what we clearly see here for the 100-meter dash, here we see at the very beginning this upward sloping, what's called an acceleration region. We see a middle part, or approaching the middle part of the race, as called the linear region. And so the linear region, we can derive velocity and acceleration not just from the linear region, but from the entirety of the graph. And so the linear region would essentially be that part of the race where the athlete is achieving a fairly consistent change in position with respect to time. And so, in how we derive velocity and acceleration from this graph is going to be the subject of the next two slides. The third and final phase of this particular method is referred to as the deceleration region. So we're going to use a simple body weight squat to illustrate this graphical approach. And so we're going to start by tracking the center of mass of this particular exerciser. So the red dot here we see the center of mass roughly at around waist level, but as this person moves into a squat position, we see the vertical position of the center of mass moves downward, and then it moves back upwards as this person moves back into the starting position. So we're going to graph that change. So if we track that position, of course, with respect to time, we're going to put time on the x-axis, and with a kinematic analysis, we always start with position. In this case, we're not concerned with horizontal position because the person is staying in one spot. So we're just going to track the vertical position of the center of mass. And by tracking that position as a function of time, we will be able to determine velocity and acceleration. The graphical method to answer how, the graphical method that we'll cover on this slide and the next will step us through that process. So what we've done here, and I've expanded it, I've stretched it vertically to highlight unique regions here. So I've taken this pattern and plotted it on this graph below. Now, when we conduct a kinematic analysis, we need to reference various parts of this graph. So we have three axes, three x-axes, all of which have the same measure. It's time in seconds. The first axis is vertical position. As we move down, we have vertical velocity, and we move down once more, we have vertical acceleration. In this order, we never change this order whatsoever. So we always have to examine the vertical position, which we did on the previous slide. So we want to identify some key areas with the graphical method here, or rather key points on this movement pattern. And so we have point A, which is the beginning, we have point B, point C. The unique similarity between these 3 points, with point A you can see here fairly flat region, point C fairly flat region, point B fairly flat region. And so if it's flat on the position time graph, that indicates that if there's no change along the y-axis despite a change along the x-axis, any calculation, the kinematic calculation, will be zero. There's a zero vertical change. For B, here we see no vertical change. For C, no vertical change. Now, the other important characteristic with B is that this point here indicates a change from a movement in this direction to a movement in the opposite direction from a graphical perspective, and that's going to be an important consideration. So at this point, even though it appears flat, it can be even appear as a sharper, rounded region here, but when it changes from going in one direction to the next, we would indicate that over a very short period of time, it's going to be a horizontal line, or it's going to be described as a horizontal line. So once we identify those points where we see no change of the y variable, we draw a dotted line that extends all the way through the x-axis for the next two variables, as we see here. And then we know that at this point, if there's zero vertical change, remember the equation for velocity, it's the change in position, and in this case the change in position is going to be zero. So we know that vertical velocity at this point is going to be 0 meters per second. At that instant in time, remember this is just a single instant in time. Likewise, we know that when we have this very, very short interval of time, as this direction transitions to an opposite direction, it has to move through a period where it's flat or a period where the slope is 0. Likewise, we know that at this instant in time, because there's no vertical change, the value is going to be 0. But just like walking down a hill or running down a hill, we see that the hill becomes steeper and steeper, and then it flattens out. That point where the line is steepest is the point that we define next, just visually. So we don't have any numbers here. We're just making a visual estimation. As you run up a hill, we know that it's not so hard. Then it becomes extremely difficult at the steepest point in the hill, and then it becomes a little bit easier as the hill starts to flatten out. And so we just eyeball where we think that slope is steepest, and we would draw a line through that very steep part, draw a line through that very steep point where we think it might lie right here, and then we would draw two more vertical lines that cut through the other two variables. It's one last point to make here, because this line is going in an inverse direction, this line is going in a direct direction, the value that this point takes will always be positive, because positive x, positive y. In this case, you have positive x, negative y in terms of its direction. So this value is going to be the peak slope. This will be the peak slope, but in opposite directions. So then we would put a point here on the negative side of velocity, okay? And we just arbitrarily would just put a point where no other point in this entire region would be less than this one. So we know this is where velocity is going to be most negative. Likewise, this is where we know velocity is going to be most positive, and the most negative point, we know that there's going to be a direction change. We know that there's going to be a direction change on the most positive part. And so by making a change from 0 to peak negative, then we go from peak negative to peak positive, and you have to move through the 0 point here. And then we go from peak positive back to 0. And so what we see here is we take the exact same principles for position and we apply it to the velocity pattern. And so here we have a 0 velocity. Here we have a transition from this direction to another direction, which is the flat line. That would be a 0. This would be a 0 acceleration, because now we're going to move to acceleration. Likewise, here we see a flat line, which is not a 0 velocity, it's a 0 acceleration, because we see over a very, very short interval of time, 0 change in vertical velocity. But the 0 vertical velocity here does not translate to a 0 acceleration because we have a slope here. We have a slope here. We have a slope here. So look for those, eyeball those points where we have where you think a peak slope occurs, and then pay attention to whether that slope is direct or positive or inverse negative, inverse negative. And then find those slopes, and here we already have a dotted line coming through this point. We add 2 more dotted lines, and now we add the points where we have peak negative. We have 0 for this point. We have peak positive defined by the black line. We have a flat point, which the slope of this line cutting through this isolated point is going to be 0. And we have a peak negative here. And now we just connect all those dots using curved lines. We never use straight lines. We never use straight lines because those would create something called discontinuities at the change in direction points. So this ends the second part of our third module, ending with the graphical method for the kinematic analysis.